Okay, so we're going to talk about limits. We're going to do one more example of finding limits with graphing, and then we're going to talk about continuity as well and how those two are related. So we're going to go through these limits pretty quickly because we already went through a couple of examples. So to start off, this first one, this says that the limit as x approaches 1, remember from the left of the function. So here's 1. Now to the left of 1, notice that there's nothing here. And so what that means is you can't come in from the left. So this limit does not exist. But now if you're coming in from the right, well, that one's pretty easy. If you come in from the right, it's approaching 9. Okay, now the limit as x approaches 4 from the left, so if we come in, here's 4. From the left, that function is approaching 1. And then from the right, if we come in from the right, this function is approaching 9. Similarly for 6, from the left, the function is approaching a y value of 6. And then from the right, this function is approaching a y value of 9. Okay, now the limit as x approaches 8 from the from the left. So here's 8, so from the left, this function has a vertical asymptote. It's going towards positive infinity. And from the right, this function is going down towards negative infinity. Okay, now let's do the infinite limits. The limit as x approaches negative infinity, so if we look over here on this way, we see that the function is not defined over for values, x values less than 1, so this limit simply does not exist. Now on the right side, however, notice that our function has a horizontal asymptote here, and as x goes to positive infinity, over on the right side, this function is getting closer and closer to a y value of 8. So that's the horizontal asymptote. Okay, now let's talk about continuity. And let's write down the definition of continuity. Okay, so a function, I'm going to write it down right here. A function is continuous at x equals a, so a is the value that we're checking for continuity, as long as the limit as x approaches a of the function is equal to the value of the function at that point. Okay, so let's see what this means. I mean, basically what you do is you find if you're trying to figure out if the function is continuous at a point, you find the limit as x approaches that point, you find the value of the function at that point, and all you need is for those to be equal. Sounds simple, right? Okay, so let's try it. So we want to know if f of x is continuous at x equals 3. So here's 3. And so we have to find both of these. So intuitively, if we look at the picture, we would say, well, yes, right? It is continuous right there. Well, let's prove it. The limit as x approaches 3 of the function is equal to what? Well, remember, to find the limit as x approaches a value without coming from the left to right means you have to find it from both directions. So if you come in from the left, this as x approaches 3, the function is approaching let's say, so that's about, I don't know, 3.8. And then we compare that to the value of the function at 3. So f of 3 is equal to, well, that means we just go up to 3 and go to the y value, which is exactly the same thing, 3.8. So this proves that, yes, the function is continuous at 3. Now at 4 we have a problem though, because notice that the limit as x approaches 4 of the function, if we come in from the left we get 1, if we come in from the right we get 9. This means, since it's different, that this limit does not exist. And the value of the function at 4 is equal to, right here, this is the solid dot, equals to 1. Now obviously these are not the same, so that means that it is not continuous. And this type of a discontinuity is called a jump discontinuity. Okay, now what about at 5? Well, similarly, we do the same thing. The limit as x approaches 5 of the function. If we come in from the left and we come in from the right, we'll notice that from both directions it's going towards 6. And if we try to find the value of the function at 5, it's going to 6 as well. So that means, yes, it is continuous at x equals 5. Okay. Now what about at x equals 6? Well, the limit as x approaches 6, you'll notice, same thing as what happened on number 12. There's a jump discontinuity. This limit, since it's different coming in from the left and the right, it does not exist. And the value of the function at 6 is equal to 6. So that means that it is not continuous. Okay, so if we want to give all the points where the function is discontinuous, we would say that it's discontinuous at, we found here that at 4 it's discontinuous, and at 6 it's discontinuous. And if we look at the graph, we have here also a discontinuity at 8. This is a infinite discontinuity. Okay, so now let's say we want to express in interval notation all the x values such that f of x is continuous. So we're just going to write down where it's continuous in interval notation. So we'll start off where our function starts, which is right here at 1. So we're going to go from 1 all the way up to our first discontinuity, which is at x equals 4. So we're not going to include that one. And we're going to join that with, now we start back up at 4 because it's after 4 it's continuous, but not including 4. All the way to 6, where we have another discontinuity. And then from 6 we're going to go all the way up to 8, where we have another discontinuity. And then from 8 on, 8 all the way to infinity, the function is continuous. Okay, so now what we're going to do is we're going to use a graphing calculator to find the limits. This is useful when we aren't able to find the limits analytically. So let's get started. Now this first one is the limit as x approaches 0 of e to the 2x minus 1 over x. Now we don't have any tricks yet to find this one. So let's grab our calculator and try to figure this out using a graph. So the first thing I'm going to do is I'm going to put this function in. I'm going to go up here, and then I have e to the 2x minus 1. Now here I want to divide all of this by x, so you have to be careful. This means that I have to put this entire numerator in parentheses. So let me go back and insert a parentheses, and then divided by x. Okay, so we have that now, and let's just graph this to take a look at it. So we can see here, so we're trying to find the limit as x approaches 0, so let's try to get a closer look. Let's zoom in. And let's put the center right here where we see our graph. And so if we look at this, the limit as x approaches 0, let's trace it. Notice that when x equals 0, there's no y value. That should be obvious, because notice that if we plug in 0 into here, we get that it's undefined at 0. But that doesn't mean the limit doesn't exist, because as you get closer and closer to 0, and let's zoom in even more, you'll notice that the function gets closer and closer to 2. So that means this limit is equal to 2. Now another way to see this is by using a table. Let's go take a look at that. So I'm going to go to second, table set, and table start. When you're trying to find a limit, make table start the value that x is going to. So in this case, since x is going to 0, I'm going to use table. I want table start to start at 0. And this is the scaling that you want. So since we're trying to get really close to 0, you want to make this number small. So I'm going to do 0.01. Okay, so then I'm going to go second table, and let's take a look. Okay, let me go back here. Sorry about that. So make sure, keep those at automatic. Okay, so here's 0. Now obviously there's no y value at 0. It's undefined. But notice that as you're coming in from both sides, this guy is approaching 2 and this one is approaching 2. So that's that one. Okay, now the next one, let's draw a picture of it. Again, the numerator needs to be in parentheses. So we're going to do x squared minus 4 divided by, and then again parentheses for the denominator, x minus 2. Now you might recognize this one. This one we can actually do analytically by factoring and simplifying. But let's do it by graphing, and then you can try to see if you get the same answer by factoring. So here, let's take a look at the graph. Now I'm going to go zoom standard so that we can look at the whole thing. Now this time, I want the limit as x approaches 2. So when I zoom in, I'm going to get closer to x equals to 2, which is right around here. So there's my x value. I'm going to go zoom in right there. Okay, so now I'll trace. And here's x getting close to 2. And we can see that it looks like it's going towards 4. And you can zoom in as many times as you want. So this guy is going towards 4. And again, if you factor, you'll see that you get exactly the same thing. Okay, now let's try this last one that we have here. We have e to the 2x minus 2 minus 1 divided by x minus 1. Zoom, standard. What does it look like? Aha! Did you catch it? My mistake? Let's go back. What did I miss here? What did I miss? What did I miss? What? Ta-da! Okay, good. Parentheses. Good job. Okay, so let me insert parentheses here on the numerator. Now make sure you press insert so that you don't erase the other stuff that you had. So insert parentheses, insert. Actually, that one I didn't have to. But this produces a much different picture than the other one. So you got to be careful with that. Make sure you put your parentheses. Okay, so let's go back. Let's take a look. Where are we going? We're going to x as x approaches 0. So let's zoom in at 0. And it looks like, let's trace here. As we approach 0, looks like we're going to some funny number here. So let's zoom in a little bit more. Okay, so if we trace it, what do you notice here at x equals 0? Well, you might notice that it's actually defined at x equals 0. And you'll also notice the function is continuous, so this is simply equal to e to the 2 times 0 minus 2 minus 1 all over 0 minus 1, which is approximately equal to 0.8647. So in this case, it's continuous, so we can simply plug in 0 and we get the answer. Okay, so for the next two problems, we have a piecewise function here, and this one we're going to have to convert it into a piecewise function so that we could see what the limit is. Let's do this one first. So the idea is that we want to find the limit as x approaches a from the left and from the right. So here for this one, a is equal to 3. So what we're looking for is the limit as x approaches 3 from the left and the limit as x approaches 3 from the right. Okay, now we're going to do this algebraically first. So let's write this down here on this piece of paper. So we have f of x is equal to x squared minus 2 from 0 to 3, 2 when x is equal to 3, and 2x plus 1 when x is greater than 3. Okay, so if I want to find the limit as x approaches 3 from the left, well, since I'm approaching from the left, what that means is that I'm looking at numbers that are less than 3. So if I take a look at these, this function is defined to be x squared minus 2 from 0 to 3, 2 when x is equal to 3, and then 2x plus 1 when x is greater than 3. So since these are numbers that are less than 3, then which one of these 3 would I use? Exactly. This one. So this means that I'm going to plug 3 into that first one. And that's going to give me 7. Okay, now let's do the same thing from the right. The limit as x approaches 3 from the right. Let's do blue. Okay, so if I'm coming in from the right, well, that means that these numbers are greater than 3, which would mean that I'm going to use this one. So I'll plug 3 into there, so I have 2 times 3 plus 1, which is 7. So this isn't asked in the question, but let's just state it. If I want to know what the limit as x approaches 3 of the function is, remember this means you want to look at both sides. So since from both the left and the right it equals to 7, then that means the limit exists. And it equals to 7. Okay, now that's all fine and dandy. But let's take a look at the picture. Let's see what it looks like. Let's do the graph. From 0 to 3, not including 0 or 3, the function is x squared minus 2. So this is a parabola that's shifted down by 2. So at 0, this guy equals negative 2. At 1, this guy equals negative 1, and then right here somewhere, this is going to cross. So we have this circle, and you'll notice that at 3, if I plug in 3 here to see where it's going to be at x equals 3, we would get 7. But not including the value at 3. So at 3 it's going to equal 7, so I'm going to put a open circle there. And I'm just going to kind of continue on here. Well, that was pretty good. Okay, so that's what that first part looks like. Now we have this one. When x is equal to 3, the function is equal to just simply the number 2. So at x equals 3, the function is equal to 2, so that means we would have a solid circle there. Okay, and then after that, for x greater than 3, it equals to the line 2x plus 1. So I'm just going to plug in a couple of values. I know that at 3, this line is 7, so here. And then, but it's not including 3, so that's why we would have an open circle again. And if I plug in, let's say 4, I would get 4 times 2 is 8, plus 1 is 9. So when x is equal to 4, this guy is equal to 9. So this is the straight line. It looks like that. Okay, so question. Is the function continuous at 3? What do you think? Dun, 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 dun. Is it continuous right here at 3? What do you say? That is correct. Nope, it is not. Because the limit, as you approach 3, although it exists and it equals 7, the value of the function at 3 is equal to 2, so those are different. So that means that it is not continuous. Okay, now let's go on to the next function, this guy right here. And so we're going to find the limit as x approaches 4 from the left, and the limit as x approaches 4 from the right. Now, although this doesn't look like a piecewise function, in reality, it can be described as a piecewise function. Because this guy, so let's convert remember that the absolute value of x can be described as a piecewise function. Remember that what the absolute value does is it turns every number that you plug into here into a positive number. So what that means is that, let's say x is greater than 0, then that means that this guy right here would equal to x. So for example, if I plug in positive 4, that equals to just 4 as well. So that's exactly the same thing. Now, if x is less than 0, however, this absolute value is going to turn it into a positive number. Well, how do you turn a negative number into a positive number without the absolute value? Well, what you can do is simply multiply it by a negative sign. So these two are basically, what you're saying is that they're equivalent. Okay. So, if this doesn't make 100% sense, try plugging some numbers into this one and plug it into the piecewise function and see if you get the same thing. Now, you might be wondering, what about at 0? Well, we can put that it equals to this guy when x is greater than or equal to 0. Because it's actually the same at both, so it doesn't really matter. Because when you plug in 0 into this guy or this guy, you get 0 each time. Okay, now let's talk about this one, though. Let's try to turn this function into a piecewise function. So let's first of all write down what absolute value of x minus 4 is. Well, the idea is the same. The idea is that when this guy, this whole inside, when x minus 4 is greater than 0, when this guy is positive, this guy is going to equal to x minus 4. So what this tells you, if you bring the 4 over to the other side, is that if x is greater than 4, that means this guy is going to be positive, which means these two are equal. So that one's pretty easy. But now what happens if x minus 4 is less than 0? Well, if x minus 4 is less than 0, that means this guy would be negative, but this is telling you that it's always going to be positive. So if this is always going to be negative, then you need to multiply the entire thing by a negative sign. So this would be negative x minus 4 when x is less than 4. Okay, so if that's what this guy is, then that means that absolute value of x minus 4 divided by x minus 4 is equal to, so let's do it one by one. Here we have x minus 4 when x is greater than 4. So this would be x minus 4 over x minus 4 when x is greater than 4. And this would be when x is less than 4. This would be negative x minus 4 over x minus 4. Well, lo and behold, what this means is that this guy is actually on top. This is equal to 1 when x is greater than 4. And negative 1 when x is less than 4. So this is what this guy up here simplifies to, which is pretty crazy if you think about it. So now finding the limits is really easy, because if you wanted to know the limit as x approaches 4 from the left of our function, well, you look at numbers that are on the left less than 4. So this is equal to negative 1. And if you want to know the limit as x approaches 4 from the right, that means you're looking at numbers that are greater than 4, which means you would use this one, so this is equal to positive 1. Okay, now if we try to graph this guy, what this guy looks like, this guy is, we said earlier, is 1 when x is greater than 4, and negative 1 when x is less than 4. So now notice that x can't equal 4 in this case, because 4 would make this function undefined. So that's why we don't have it equaling 4 in either of these. Okay, so when x is greater than 4, it equals to 1. So it equals to 1. When x is less than 4, it equals to negative 1, which is down here somewhere. And so that's what the function looks like. If you come in from the left, you get to negative 1. If you come in from the right, you get positive 1. And that's it.